All right, well, so our next speaker is Bonaca. Anna got her PhD from Yale in 2016 and is now an ITC Fellow at the Harvard-Smithsonian Center for Astrophysics. And in her talk today, she'll be telling us about uncovering the nature of dark matter.
Thank you. So much like the Nobel Prize this year, the first session of the BashFest spans like the range from exoplanets to cosmology. So I thought I would begin with this beautiful image of the night sky seen from Big Bend, just to set the stage. So far we've been hearing about what we can learn from studying individual stars. And in this talk, I'll be showing you how we can use collective motions of stars in the Milky Way, many of them seen here, to learn about the internal structure of our own dark matter halo. And it is an important question that has for a long time been kind of purely in the realm of cosmology, but thanks to the Gaia mission in the last year and a half, we've really had a lot of progress done here in the Milky Way. So it's really a pleasure to share some of this excitement with you. And so the reason why I want to test the cosmological model is because it looks fairly well on big scales. So in this movie, I'll be showing the distribution of dark matter halos in an n-body only simulation on the left side and of SDSS galaxies on the right side. So you can see that on very large scales, the distribution of dark matter halos and galaxies is statistically very similar. And this is one of the big successes of lambda CVDM as a theory. So this made people want to test this model on smaller scales as well. So once people realized this good agreement on large scales, they started zooming in and look into those individual halos on their own. And so something like 20 years ago, people realized that the internal structure of a dark matter halo, shown here on the left, should be full of this small subhalos, full of substructure. However, when we looked around the Milky Way galaxy, we see some satellites, some dwarf satellites, but not nearly as many. And this was dubbed the missing satellites problem, and really has its 20th anniversary this year. Of course, in the meantime, we've realized that this was not really a one-to-one or apples-to-apples comparison. So what I'm showing on the right is the dark matter only simulation, and on the left and on the right is what we see in the light and the stars around the Milky Way. This was, of course, simulating gas physics, and simulating stars is really hard, which is why it wasn't done 20 years ago. But in the meantime, there has been a lot of progress. And so now I'm showing a simulation, a very high resolution simulation from Andrew Wetzel and the FIRE team that has many people in this department as well, showing what is our state-of-the-art look at the Milky Way side simulation at the present. And so now, seeing this in light, it looks very comparable to what we see around the Milky Way. So statistically, there is no more the missing satellites problem. The number of luminous satellites in a simulated galaxy really matches well to what we see around the Milky Way. And really, the solution to this missing satellites problem has been that many of those satellites that are predicted to be present in dark matter are just completely dark. So when we look into this simulation, just forget the light, and look into the dark matter side, we still see that those subhalos are present. There is still a lot of structure in the dark matter. It's just completely dark and invisible to us. And this is a very generic prediction of the lambda CDM cosmology. And it is so important that a couple of years ago, Mike Billenkolchin here and James Bullock kind of issued a call to the community saying that this is our most urgent calling to find those small clumps of dark matter below the threshold of galaxy formation. And they motivated this search with this power spectrum in different models of dark matter. So in this standard cold dark matter scenario, we are expected to have continually rising abundance of small subhalos as we go to the, over here, lower masses. So this is just a power spectrum or abundance as a function of mass. And so in the cold dark matter case, we see that the curve continues rising all the way to something like an Earth's mass. If the dark matter particle is lighter, then this curve starts peeling off. And so basically measuring where this edge, what is the lowest mass dark matter subhalo, can tell us directly something about the nature of dark matter. And so, as we saw, we know that the small galaxies around the Milky Way are surrounded by dark matter. So we can put some constraints on what is the lowest mass dark matter subhalo that exists in this regime between down to the 10 to the 9 solar masses. And that rules out some of the models, like some warm dark matter models of 1 keV are now excluded. However, there is still a lot of the parameter space left over here. And what we'd ideally want to do is really find out if there are any dark matter subhalos down to those masses of 10 to the 7 or 10 to the 6 or even lower solar masses. And so we've got our work cut out for us. So we saw that the solution to the missing satellites problem is that those are all dark satellites. They are low mass, so they only have a small effect on what we on any observables that we actually see. And there are different ways of approaching this. So there are some, we know that we can map matter in the universe through gravitational lensing. This is like a whole other talk that someone else could be giving. What I'm interested in is to see if there are any signature of such substructure in the halo of our own Milky Way. And so we saw in those visualizations that the substructure should be more abundant in the outskirts. And what I will be using as a tracers are tidally disrupted globular cluster. And to show why, I will show here animation of a tidal disruption of a globular cluster that initially is completely bound, represented by a dark dot over there. The Milky Way disk is seen edge on, and the star is the position of our sun as a reference. And so, as globular clusters orbit the galaxy, stars are continually escaping through the Lagrange points through evaporation and tidal stripping. And so from the one Lagrange point closer to the galactic center, the stars lead off, get a lower energy, and kind of move in front of the cluster. On the other Lagrange points facing away from the center of the galaxy, the stars that are escaping are kind of lagging behind. And this whole process is kind of barely happening. Those stars are only barely escaping. So they have still pretty similar orbits as the cluster itself, just like a little bit extended. And this is important because it actually is a reason why the structure that forms is so thin and narrow and kinematically cold. So these are important tracers because then they're very sensitive to any perturbation we might see because they're intrinsically, we know they should be fairly cold. And so in this case, in this model, I only used a smooth galaxy, which would be something like a warm dark matter case. And then this tidal stream that formed is very, very smooth, and basically it is a one-dimensional structure in some six-dimensional space of positions and velocities. As a comparison of what we would expect if the dark matter halo was clumpy, we can then repeat this experiment, just not in this analytic gravitational potential, but in an actual n-body simulation that has a full cosmological inflow of dark matter subhalos that are like continually interacting with the stream itself. And in that case, we might find something that looks like this. So while the general shape of the stream is kind of similar because they were placed on the same orbit. And in this youngest part of the stream, it looks kind of similar to what we see in the top. I see that the stream overall is very different. There is a lot more structure in this stream that has formed in a clumpy galaxy. There are density variations like enhancements and underdensities or gaps. There are stars that are like kicked out of the main stream, and even some parts of the stream like over here that seem completely detached from the rest of the stream. And so this is kind of what we want to then, this is the experiment we want to, or this is the observation we want to make in the Milky Way. Are the stellar streams in our galaxy, do they look more like the one case on the top or the case on the bottom? And luckily, we do have tracers in the Milky Way. So here is the view of the stellar halo of the Milky Way, seen at different distances that map to different colors over here. And so the bound structures, like those bright clumps, are still bound dwarf galaxies and globular clusters. But what I want to really you to take away from this picture is that the stellar halo is not uniform. There's a lot of these streams, like very elongated features crisscrossing it. And so the most prominent one is over here in the bottom, and this is the tidal debris of the Sagittarius dwarf galaxy. So we can actually, in this, for people familiar with SDSS, they recognize the footprint. It actually has been wrapped in other surveys to go all around like 360 degrees. And traced to the Sagittarius dwarf galaxy. But in addition to the Sagittarius, there's a lot of smaller accretion events. So for example, this stream over here is called the orphan stream. Orphan because we haven't actually mapped it to any dwarf galaxy or globular cluster, but we think it is like just based on the width, that is slightly lower mass than Sagittarius, but still a dwarf galaxy. And what we will be using throughout the rest of this talk would be streams such as those forming, like currently forming from the globular cluster Palomar 5 over here. So you can see that the cluster over here and the tails extending from either side of it. And the object that I spent most of like the last 18 months studying is called GD1. I hope you can see it like this faint arc on the right side. So we think based on its width that it is actually a disrupted globular cluster because it's so thin, but we actually don't see the progenitor, the cluster itself, so we think that it's actually completely disrupted globular cluster. And so before the Gaia data was released, our best view of this stream came from this study from Sergei Kapasov in 2010, where he created a matched filter, so tuned to reproduce this stream itself. So basically, what this image is showing now in coordinate system oriented along the stream, such that the stream should be at this coordinate phi2 of 0, is that every pixel has a weighted number density of stars, and the weighting is done that it's preferentially selecting basically main sequence turn of stars at the distance of this stream. And so what you can take away from this figure is that there definitely is a stream detection. So there's like a clear overdensity of stars here. And there seem to be some density variations. So we're like very excited, like thinking, oh, maybe this is a gap. Maybe this is what we've been looking for. However, it's kind of hard to know whether this is intrinsic to the data or something to do with the foreground contamination. For example, you can see this variations of that level even in off-stream fields. And then our view kind of completely changed in April last year, because in addition to colors that were used to select the main sequence stars in the CMD so far, what Gaia mission provided us is the motions of stars as well. So in this image of just like the animation of the lowest nearby stars, we can see that you can isolate stars that are like moving together from a cluster, not just based on their colors, but also on their motions. And of course, this is just for the 6 million or so stars that have 60 positions and velocity in the Gaia data set. So for the stars that I'm interested in further out in the halo, we don't have data that is quite exquisite. But still, we have a lot more information that we had before. And so I was very excited, and like the first day of the data release, to join Adrian Price-Quillen at the Flatiron Institute and try to look at this tidal stream, the GD1 stellar stream, again with the eyes of Gaia. And so I'll just walk you quickly through the steps that we took. It's really fairly straightforward. So we first only selected distant stars that have parallax smaller than 1 milliarc second, and showing that same kind of region of the sky. Don't see much, just like the density gradient when we are dipping into the stellar disk on the left-hand side. However, when we take those stars and look into the proper motions, we see that proper motion along the x-axis versus y-axis is very structured. And it turns out that this over here is the stellar halo, this is the disk, and this outlier over here turned out to be the GD1 stream. So when we selected stars in this box, we already got the stream itself to pop out where we expected it to be. However, what we also had is still all of the photometric information that we haven't used. So when we further look into the color magnitude diagram of these stars, we see that there is a clear main sequence and a turnoff over here. So just selecting stars that are more likely to be members of GD1 over here, we get a map of GD1 that is now much cleaner than the one that we had before. And you can see that like a couple of big differences from before. We used to need to bin the stars. Now we can actually plot individual stars as highly probable members on the stream. And for the grad students in the audience, I just want to stress that as a grad student, I made that map of SDSS finding substructure, and it took kind of like a whole semester to tune the match filter and to get that map to work. This took 2 days. So if you have a way to fold in Gaia data in your research, have a look. It's really an awesome data set. What we found in GD1 is that now that the levels of contamination from the Milky Way are much lower, and we were actually first able to extend the stream for more than 20 degrees. Then all of the density variations that we saw, like these two gaps, we can say like, yeah, they're actually associated with the stream. They're not a signature of any contamination from the Milky Way. They also look different. The one on the right looks completely empty, so I think there might be, that might be where the progenitor used to be, and is now completely disrupted. But what surprised us the most was that there actually seemed to be a couple of spots where there's an overdensity of GD1 stars beyond the mainstream. And so it is kind of subtle, and when I talk to a more physics-based audience, they wonder whether this is actually a significant overabundance of stars that look like in this more linear spur and more fuzzy blob on the bottom. So what we can then do is calculate what is the membership probability to the stream, assuming a constant background as a function of phi1. And when we do that, we see and only plot stars that have membership probability larger than 50%. We see that these stars over here and in the bottom are actually statistically significant above the background. And then, of course, we were wondering, okay, what can we do? what we should have been expecting. Now with the GA data, we also have very good constraints on the orbit of the stream. So we, in the smooth model, created a model of, in the smooth Milky Way, we created a model of the GD1 and got a model that looks like this. So by construction, we disrupted the progenitor at this location. So we matched one of these gaps to that. But then the rest of the stream looks fairly regular, whereas in the data we see a lot of structure like this gap and this additional spur. And now that we are actually confident that this is associated with stream, we wonder, like, can we do it? Is this signature of dark matter? And so there's been a lot of research done previously in these interactions of stellar streams with dark matter substructure. And this is just one compilation from Yoon et al. Paper in 2011, where they show different configurations, and basically all of the streams have encountered the dark matter subhalo at the location of a gray cross. And so you can see that it usually is associated with a gap in the stellar stream. But in this one case, there also looks like there is a stream fold over here. So even though like the morphology is complex, really the community adopted the gap in a stellar stream as a signature of dark matter. And there's been really a lot of research, many papers, probably incomplete list, showing how properties of a gap in a stream changes with the velocity of the encounter, the impact parameter, the mass of the subhalo. But there hasn't really been a lot of research done what we can learn from this additional feature. And so to do this, to study this in more detail, we then revisited this model of GD1 orbiting the Milky Way, and then had it encounter a small clump over here and followed what happens afterward. So you can see that it pulls out stars in this ring that precesses around the stream, has a gap, and then when we evolve it to the present and see in projection, it actually looks like a lot of the stars are kind of displaced from the mainstream. Observed from the Milky Way's point of view, now we have the observed stream on the top and the model on the bottom, and we see that it qualitatively reproduces what we expected to see. So it does have both a gap and this spur of stars. And what we are really excited about is that the parameter of the impact listed here are in this cosmologically interesting regime. So we did require an object of 5 million solar masses. So it is really where we wonder like whether this could be a dark matter subhalo. What you'll note is also that the scale the size of the object is very compact. So we wanted to understand like what sort of what range of values is allowed in these parameters, given that this is just a single kind of draw of the possible options. And so to study this in more detail, I will now adopt that value, those values I shown as a fiducial, and they will always be shown in the middle row over here. And then in every column, I'll be changing one parameter at a time. So changing and fixing everything else to the fiducial value. So if we change the time since the encounter and look in this idealized simulation, we can see that at early times, if the encounter was very recent, we would only have like a small loop of stars and like a small gap, which expands as time goes on, and this loop gets bigger as well. But what you'll notice is that this loop also gets more aligned with the stream. So the fact that we see kind of this spur of stars sticking out from the stream already tells us that it had to have been a fairly recent encounter. So next, when we look into see how the structure of the stream changes with the mass of the perturber, you see that both the size of the gap and size of the loop are increasing with the mass of the object, which is not surprising. For the impact parameter, the effect is nearly the same, but not completely. So you can see that while for the smaller impact parameter, so the closer the object came, this loop is larger, the kind of gap size stays pretty constant. So this is really exciting because it tells us that with these two features simultaneously, we'll be able to break some degeneracies of this in this whole picture. Then finally, velocity is completely degenerate with the mass. For the faster encounters, we see both smaller gaps and smaller loop. And finally, for the size of the object, which is modeled just as a Hernquist sphere, you can see that, of course, the more compact the object, the larger both the gap and the loop. And interestingly, this would be something like a density of CDM subhalos expected for that mass. So we already see that it has to have been something much denser than what we would naively expect in a dark matter simulation. So we can take this and write up a model that qualitatively or more quantitatively compares the properties of the gap and the spur to these models to try and infer what ranges are available. And the parameters of largest interest are the size of the perturber and its mass. And so the gray shaded region shows where we expect the GD1 perturber to be. And in points, I'm showing some of the known objects that are orbiting the Milky Way. So you have the molecular clouds as circles, the dwarf galaxies as squares, and the globular clusters as triangles. Dark matter subhalos are here. So this is the extrapolation from the mass concentration relation. And the dashed lines are showing the 1, 2, and 3 sigma scatter. And so taken at face value, it looks like that the globular clusters are the most likely culprit. They have the largest overlap in this mass size plane. However, what Gaia data also gives us are the orbits of all of the globular clusters in the Milky Way and other objects. And so we can integrate back orbits and see if they ever came close enough to the GD1 stream to have caused the impact. And when we do that, we can actually remove all of the known globular clusters. And given this very small overlap with the space of expected dark matter subhalo properties, we are kind of left with a puzzle because clearly something happened to the stream, but we don't have obvious culprits. And so there is, we'd ideally like to know whether this is maybe a globular cluster hiding behind a disk, something that we haven't discovered yet, whether this is unusual dark matter subhalo. It also could be a black hole. You can see that like all of the limits are just continuing to the left, so it could be something very compact. And this is still a puzzle, a very much open question. And the last, some time I have left, I would like to kind of chart like three different lines of research that go out from here. So we don't know what happened to this stream. We do know that something happened. So we have really, I think, the most exciting opportunity to follow up dark matter subhalo. So I'll be talking about it first, how to study this individual object. And to do that, I think we'll need to move past. So all of the constraints I've placed so far on what we know about the encounter just came from this spatial distribution of stars at the present. So the fact that there is a gap over here and there is a spur of stars sticking out of the stream. And when I take different models that kind of fit well and overplot them in different colors of gray, they kind of have the same distribution. What they have different is actually a radial velocity. So in one case, there is no radial velocity offset between this main part of the stream and the spur. And in the case of these black points, there is a positive radial velocity signal, and in the darker gray is a negative radial velocity signal. And that is important because if we can measure the radial velocity offset between these components, we might be able to predict where the object should be at the present. So here I'm showing, like on the sky, where the predictions are for this object to be in those different models. And it would be really exciting if we can, like, sort of in a vein of LIGO, predict, oh, there is something interesting in this region of the sky. You might go have a look if you see any different signatures of this event. So to do the measurement, you'll see that on the y-axis, the radial velocity signals are not the biggest. So of course, like for exoplanets, yeah, this is huge. Or any other area of astrophysics, probably not so much. So we used hectoshell spectrograph on MMT and I'm always just showing some very preliminary data over here. So we observed 4 fields in the mainstream shown in the light orange, and 4 fields here and in the spur shown in dark orange. And it looks like there is not much radial velocity offset between those fields that are kind of in parallel over here, but there is some scatter that we are still trying to understand. So as we're working on it, we are hoping, to constrain whether the model is looking more like this or more like that, and then actually put other constraints in the model and make predictions of where the object should be at the present to go follow it up directly. But this is always going to be, even though it's my exciting object right now, it is always going to remain just a single object, and we do expect a full population of dark matter subhalos to orbit around the Milky Way. And so what we'd ideally like to do is see signatures of such interactions in other streams as well. Oh, I should also say, we have a HST promotion program going on to not only measure the relative radial velocity between the spur and the stream, but also a very precise HST promotions and like this and 2 cycles. But moving on to other streams, this is, I think, the next direction we can take. And I'm showing here a detailed map of the Palomar 5 stream that I shown earlier, that was in the corner, now seen in the legacy surveys data taken with the dark energy camera. And what you can see here is now that the stream looks very kind of different, qualitatively different from what I've shown before. Now we can also see that there is a gap over here, there's a gap over here. It looks like there's a widening on one end and not on the other. And all of this was really enabled by the very deep photometry that we have in this region of the sky. The all as it says data kind of petered out, and the G of 22, and all this data goes down to 24th magnitude with very high precision. And this is important because it's kind of like halfway to LSST. What we're hoping to do in with LSST is that even in single epoch, we'll have something like that for all of its footprint, and then after 10 years, we'll have something like 2 or 3 magnitudes deeper than this data set. So we'll actually be able to perform studies like this, not only for one stream, but actually the full population of streams within the Milky Way. But then again, we'll only be like studying what we see in the Milky Way. And I wanted to end on something moving beyond our own galaxy, since there are also so many extragalactic astronomers in the audience as well. So this is the work I've been involved with the Dragonfly team. led by Peter Van Dockum and Colleen Gilholly, that took very deep observation of this galaxy NGC 5907 with the Dragonfly telephoto array. And they mapped really in exquisite detail this tidal stream that surrounds the galaxy. And what I was interested in is to see what we can learn about the structure of the dark matter halo from this outside perspective. So unlike in the Milky Way, we only really have this 2D view in projection, but already we can, just taking this, we can create a model of the stream that kind of looks well. So just taking what we know about the distribution of cellular light and the velocity rotation curve in the galaxy, I just took values published in the literature, set up the coordinate system so that this is kind of completely edge on, and created a model of the stream that fairly well represents what we see in the data. And so this is in case of the spherical halo, and you'll see that there is like this little offset on one side of the stream. So what we can do is like change the model to an oblate halo and see like, this is going in the wrong direction, the offset is larger. But if we take a prolate halo, we see that the stream matches much better what we observe in the data. So even if this is like very much baby steps at this point, it does look like that we'll be able to extend this modeling of the 3D structures of dark matter halos that we've been really up to now employing in the Milky Way alone to other galaxies as well. That's really very exciting because there are upcoming deep surveys that will map outskirts of other galaxies. In particular, I think WFIRST will be important there, and a lot of room for the 30-meter telescopes to provide some additional kinematic data that will further constrain these models. So I think it's really exciting times for understanding the nature of dark matter with like the tracers we have locally, and I'm happy to take your questions now. Thanks.
Okay, questions, right? Let's see, that's what I'm here filming.
Thank you. I have kind of two questions. First, if you go back to the one that showed constraints on lambda CDM satellites and existing ones. Yeah.
Mm-hmm.
So the band that basically shows the halo mass size concentration of the satellites, of halos. So can you please clarify, this is a CDM only simulation or CDM plus baryons? Second, this is at redshift 0 or at infall time. And then when I read the plot, the mass, I assume, is some sort of like criteria like M200 or something. But then going to 10 to the 4, I'm not sure how robust the results are for those low mass galaxies.
Yeah, you nicely outlined all of the future areas of work that are required. So anyway, I'll be repeating the question as I go along. So yes, this band of predictions for the mass size, and I will just like say, given all the different kinds of objects on this plot, they have different profiles, so it's more of a cartoonish lay of the land figure. So for the, as I said, for the GD1 perturber, we assume the Hernquist profile. So this is basically scale mass and scale size. For this subhalos, we are showing the NFW size, scale mass, and scale size as well. And this is taken from dark matter only, like CDM only simulation at redshift 0, and subhalos in the radial range that GD1 is orbiting, because we expect those the fluffier ones to get more easily disrupted in inner parts of the galaxy. So these are the more concentrated ones that are still surviving, but there is no there's no variance in the simulation. It shouldn't matter too much for this for this plane, but
basically make the size a little bit larger or smaller based on the feedback model that you implement in the simulation.
yeah. So in detail, in detail, it's more of a kind of order of magnitude where things are. Was there another? Am I forgetting something?
Thank you.
Yes.
So the
Okay.
other question, which is going to be short, is that so you in the last plot you showed like the prolate slash ovate shape for one of the galaxies in Dragonfly.
Yeah.
So I was wondering if you have already done this analysis or you're thinking about this of doing the same idea for the Milky Way with the tidal stream of the GD1 or PAL5. Because there have been a bunch of papers. I was wondering if with the new data from Gaia, how do you think about it?
Yes, so the question was whether this sort of modeling was done for the streams in the Milky Way, and the question is yes. I haven't done it myself, but there have been papers. They find basically spherical halo for the GD1, so the constraints haven't really changed much from the data from our findings prior to Gaia data. So our best knowledge of the structure of the Milky Way halo, it looks like it's more spherical in the inner parts, which is kind of what you expect in hydrodynamical simulations, and it looks like it's more triaxial in the outer parts. Yeah.
So you focused a lot of your modeling into figuring out what the perturb is, and I would love the fact that there's even a chance that it could be a black hole. That sounds super exciting. I would love it. Well, my questions are more about the progenitor. How much do you know about that in terms of the progenitor mass? Do you have any constraints on that or not?
Yeah, so the question is what we know about the progenitor of GD1. So we only have the estimates of like the total stellar mass in the stream, and in our models we assume something like on the order of 10,000 solar masses for the progenitor. We are now, like in the spectroscopic data that I was showing, we also measure abundances. So we're trying to, and it looks like tentatively there is a spread, like the signal to noise is kind of low, so we can't really tell in a lot of detail whether they're like how significant the spread is. But yeah, we're looking into the question of the progenitor, whether it really is a globular cluster as we've been assuming, or maybe it's a dwarf galaxy. Yeah.
And the other question is about the orbit. Is it a relatively normal orbit, as in co-rotating, or is it a circular-ish or more elliptical?
It's not circular orbit, so the orbit of GD1, that's the question, and it is, so the pericenter is at 13 kiloparsecs and APO is in like 25 or so. The important thing is that it's retrograde, so it's not, so that's, I forgot to mention, this is a crucial part of why did Gaia selection worked out so well as it did. It's because the stream is moving in the opposite direction from everything else. Yeah.
Questions? Yeah. Good.
Back to the idea of the possible role of baryons inside the perturber. If I had something like a dense molecular cloud, so instead of considering just the global effect on the density profile of the dark matter perturber, if I said it's inhomogeneous, and so I have dense clumps in it, for example, baryonic molecular clouds, would it be possible that substitutes for having a separate object, which is dense and orbiting on its own?
Yeah, that's a really interesting question about whether the structure of whether subhalos have additional substructure, and so. I think it's what I'd really like to do is to study. What we've been assuming so far is that there is like individual subhalos like orbiting in the Milky Way, but we know that there's like Sagittarius coming in, LMCs coming in. They are bringing their own hosts of subhalos, globular clusters, probably molecular clouds. So yeah, that would be one of the things, and why we are trying to constrain the orbit of this perturber to see if it aligns with any of those structures, to see if it's associated with something that is, maybe not the molecular cloud in the Milky Way, in the disk, we can rule that out pretty well, but maybe if it's like coming in with something like Sagittarius or LMC, I think that's a very distinct possibility, and yeah, we're looking into this, yeah.
I mean, even if you were just to do an artificial model, but where the perturber was not a homogeneous, was neither a point mass,
Mm-hmm.
I assume you don't, because it has a density and size, it's not a point mass.
Yeah, but we do actually use the Hernquist sphere, which in the limit of size of 0 goes to point mass. So that's exactly why we use it. Yeah, yeah.
Would it matter if you instead had it be a distribution that had an inhomogeneous lump in it?
Yeah, that's
Center of mass of that object.
Yeah, that's a great idea. So to try to model the perturber to have an homogeneous distribution of mass, we haven't done this yet, but yeah, I think that will be really interesting to see what the internal structure of the perturber, whether we can measure that from the data that we have. Yeah.
Cool. Other questions? Yeah, here we go.
I did a mental gasp when you backtracked all the globular clusters and they disappeared from your head. And of course, it's hard to do that. You have to backtrack for 500 million years. And the galaxy is inhomogeneous, at the very least from spiral arms and molecular clouds. Can you really backtrack accurately enough to rule them out completely when you include those uncertainties?
Yeah, that's a limitation of that exclusion. So the question is, how well do we know the gravitational potential, and when integrating orbits back to see if the globular cluster or any of the known objects intersected with the GD1 stellar stream. I'm looking at this as there's like nothing obvious. We did sample like the uncertainties we know in the orbits of the globular clusters, and in neither of those cases anything came closer than a kiloparsec to the stream, versus we really need something within 100 parsecs to have an observable effect. We tried a couple of different global Milky Way gravitational potentials to kind of see if that makes a difference. We didn't get any of the objects to match, but it is a very well concern. And I'm working with Gertina Beslow's group, who are trying to measure this kind of more inhomogeneous and time evolving gravitational potential of the Milky Way, taking into the account of LMC, and then trying to integrate orbits in that more realistic environment to see if that changes our conclusions at all. But yeah, to some extent, it's the best what we can do at the present, and yeah. So I think it's really important to kind of try to make predictions on the other way to see, to get more data to see if anything is consistent with that.
Great. All right. Any other questions? One here in the back.
Thank you. I actually had a question from earlier on in the presentation regarding the spatial distribution of the GD1 stream made within the Gaia data.
Mm-hmm.
And it was compared with the perturb model plot as well. So the perturb model plot actually is pretty continuous across on the left side, but the observed GD1 stream isn't. So is that a feature, or is that just due to lack of Gaia data or oversampling in the model data?
So The question is about the global comparison between the GD1, this distribution of stars observed in the GD1 and the model. So I'll say, yeah, the model is definitely not a good global model for the GD1. So we are really kind of focusing on this one local feature. We think this end of the stream is real in the data because, yeah, I think like we would be able to detect it because it gets more retrograde on this left side of the diagram. I'm not showing on the right side of the diagram. This is where we are uncertain of how long the stream is because our selection becomes more efficient because then like kind of that selection is becoming, or GD1 proper motions are becoming more similar to those of the Milky Way. So the gas selection is no longer super efficient. In the model, yeah, we could truncate the stream a little bit by making it like a younger structure. So this has been evolving for something like 4 billion years. But then, yeah, the question still remains, since we put the progenitor over there, we do predict that it should actually continue on the other side. So as a global, the model is still, yeah, not a great match to the GD1. We were just like focusing on this internal kind of local feature in the data. Yeah.
Thank you.
Any more questions?
There's time.
Yeah, sure, we'll do one more.
So those questions made me think of two separate things. One is, obviously with Gaia, the proper motions of many things are a lot better than they used to be, but I wonder if for all of the things, or maybe some of the furthest away global clusters are still iffy. So I don't know if there's some room there. And I'm guessing the molecular clusters are pretty good with radio, but the dwarf galaxies are probably still quite uncertain, some of them. Some of them got better, but some of them don't. So maybe there's some room there.
Yeah.
And the other avenue is, if something is really on the other side of the galaxy, really behind it, we know that we're missing,
Yeah.
you know, clusters and molecular clouds and things. So I mean, it's not exciting because we can't see them. That could be another avenue to
Yeah.
get some perturbers.
Yeah, for sure. As for the globular clusters, yeah, the most distant ones, like the question is like, how well do we know the orbits and proper motions for the different objects in the orbiting the Milky Way? So for globular cluster, I think it's only like 2 clusters in the bulge that we don't have good proper motions for. But for the dwarf galaxy, we're missing like half of them. There, yeah, just like not as many stars there. So yeah, that's one other thing to look into. And the data, like the Gaia data, will be getting better as it goes. Like proper motions improve linearly with time, and now the mission has been extended to 10 years, so that should be fixed. But yeah, there is always a chance that there's like something that we just can't see on the other side of the disk, and even from molecular clouds, we only see the ones that we like. They are like on this side of the galaxy. So yeah, I think this kind of underscores that it's we can, you know, it's exciting to like follow the one object, but yeah, we really want to like have a full sample from other streams. Yeah.
All right, well, let's stop there and thank Anna again.